everyone, and welcome to the first episode of Help Me Understand, a new show from Market Scale, I should say, where we are going to explore some topics and learn about some things that maybe people might say, how does that work exactly? What exactly goes on in this process that allows this to happen? And that's what we're going to do. This is a show for people who like to learn and want to learn from experts in each particular field. And so today, for our first episode, we're going to learn a little bit more about HVAC systems. How do they work? How do they keep a commercial office building cool? It blows my mind absolutely that I can sit here in an office building today when it's 100 degrees outside in Texas and the room I'm in is comfortable. It's cool. How does that work? Well, joining me today to help me understand HVAC is Jerry Taylor. He's a service manager at Boland, and Boland is the leading commercial HVAC systems, services, and building energy solutions provider in the DC metro area. Jerry, welcome to the show. Thanks so much for being our first guest.
Thanks for having me. This is going to be fun.
It is going to be fun. So, Jerry, just give us an introduction and tell us the basics about how an HVAC system works in a commercial office building. What are the basic things we need to understand?
So the basic thing that everyone needs to know is we're not making cold air. We're simply removing heat from the air that's already in the building. Heat is energy. It cannot be destroyed. It can simply be moved from a place where it's objectionable to a place where no one really cares. So think about your refrigerator at home, whether you're drinking adult beverages or a Coca-Cola. You put it inside that box, you want it to be cold. And what we do is simply take the heat out of that product or out of the box and move it to outside.
That's really interesting. So if it leaves this area, I guess that means it has to go somewhere. So in a common office building setting, where does the hot air get sent to? Where does it go?
So in most typical high-rise office buildings, we use a chilled water system to remove heat from the building. The heat that's in your office or in your IT closet is absorbed through airflow across a chilled water coil. As the warm air hits the chilled water coil, the cold water absorbs the heat and then returns it to the chiller, the heart of the air conditioning system, so they can be cooled down and pumped out again. In the refrigeration process within the chiller, that heat is removed from the chilled water, absorbed into the refrigeration cycle, and then rejected into the condenser. From the condenser, the heat is carried up to the roof through some piping and pumps and dissipated through a piece of equipment called a cooling tower. So the warm air that was in the building is now being blown up into the atmosphere on the roof where no one really cares, except for that poor guy that's up there on the roof working.
Yeah, I don't necessarily envy that person all that much, especially if you're in a place like Texas. Or I know the DC area also gets pretty warm and muggy this time of year in the summertime, and so that's not an enviable place to be, let's say. But so you used a couple of terms there that I think it would be helpful if we defined them and kind of talked a little bit more about the various components that make up an HVAC system. So what are some of the primary components that kind of make up an AC system that people should at least be aware of?
Certainly. So every air conditioning system is going to have four basic components, regardless of the capacity, the size, the type of refrigerant you're using. But each system is going to consist of at least one compressor, which is basically a pump. It's there to create a differential in pressure, pull refrigerant in at a low temperature, low pressure, squeeze it or compress it, and then put it out in a higher temperature, higher pressure gas. Step one. Step two, that high pressure, high temperature gas is pushed into the condenser, which again is where we reject heat, whether it's a rooftop unit, air-cooled chiller, or a water-cooled centrifugal. The high temperature, high pressure refrigerant that goes into that condenser is now going to be cooled or have the heat removed either through water or air contact with a coil or tubes. The high temperature, high pressure gas is going to condense, hence the name condenser, and turn back into a liquid refrigerant, as the liquid refrigerant is what it takes to do the work inside the building. So once that refrigerant flows out of the condenser, it will go through a metering device. It could be an expansion valve, it could be an actuator, it could be a fixed orifice, but we're going to meter the amount of that liquid refrigerant into our evaporator, which again is what's going to remove the heat from the place we're trying to cool. So the evaporator think about it in your home. You have a 74-degree return temperature. It contacts an evaporator coil, which is going to be somewhere in the 40s. So the air leaving that unit is going to be less than 74, greater than 40 degrees, and now we've heated up the refrigerant so we can send it right back to the compressor and continue that cycle over and over and over, hopefully for many years.
That's really fascinating. So compressor, basically a pump. That's the primary thing we need to know about the compressor then, right? And that's kind of where the whole chain gets started.
That's correct. So there are multiple types of compressors. You can have a reciprocating compressor, much like a car engine. It has a piston that travels up and down in a cylinder. On the intake stroke, the piston's traveling towards the bottom of the cylinder. It will fill with a low-pressure, low-temperature gas. As the crankshaft rotates, that piston comes back up and squeezes or compresses the refrigerant into a higher temperature, higher pressure. Then it's expelled into the condenser. Scroll compressor technology is what we see a lot of today. Fewer moving parts, and rather than that piston traveling up and down in a cylinder, you have a scroll that's fixed or welded into the top of the compressor. And then you have an orbiting scroll that is mounted on that crankshaft. And as the two scrolls mesh with one another, there's a constant intake of refrigerant, an intermediate pressure, and then a high pressure or discharge, which goes to the condenser. Helical rotary or screw compressor operates along a very similar principle. Two screws, and as they mesh together, they compress refrigerant. And then lastly, but not least, in larger capacity systems would be a centrifugal chiller. And I liken that to a merry-go-round. When you were a kid, if you stood in the center of the merry-go-round and your friends ran around like fools, you just stood there and had a good time. But the closer you got to the edge, the more that centrifugal pressure tried to throw you off of that merry-go-round. So a centrifugal chiller, again, usually it's a larger capacity, larger tonnage. You're trying to cool a very large space.
That kind of sounds like the what was it called? Like the gravitron at like the carnival, that where you're in like a circular thing and it spins so fast that it just pushes you up against the wall and then the floor drops out and you're just shoved up against the side, right? Because you're spinning so fast on the outside.
Very similar principle. So each impeller, which is a piece of that centrifugal compressor, has an eye where we're going to enter low pressure, low temperature gas. Depending on the manufacturer, that impeller could be turning anywhere from 1,800 to 40,000 RPM. So as that gas comes into the middle of the wheel, it is now being thrown, for lack of a better word, towards the outside. Many manufacturers use multiple stage compressors. So you go into the first wheel at a given pressure and temperature, and we're going to throw it out to the sides. It'll travel through a volute or some maze into the second stage of compression, where it's going to be elevated a little further. And then in the case of the very best centrifugal on the market, the Trane CVAG, there would be a third stage of compression to, again, take that refrigerant temperature and pressure to a spot where we can now convert it back into a liquid, condense it, and then do the work that we need to do.
Wow, that is interesting. So it's a multi-step process, and hearing it and hearing you explain it like this, it makes sense, but it's still a complicated process to me as someone who is not an expert in HVAC. And so my question is, in your time in the industry and in working with HVAC systems, Jerry, has this changed at all? Have there been any new developments in the last several years or so? And if so, what has changed, or has it largely been the same over the years, and we've just kind of refined and improved small things along the way?
So great questions. In the 34 years that I've been in the industry, the principle, what we're trying to do, has not changed. How we achieve making the air cooler or the water cooler has gone through a myriad of changes, from the type of refrigerant that we use. Traditional R113 machines back in the 1960s now use R514A or 1233ZD. They're different chemical components because, again, we're trying to be mindful of our environment, ozone depletion potential or global warming potentials. So we're constantly looking for better chemicals to achieve this work. The newer stuff even has some propane in it, so it makes it a little bit scary, if you're a smoker and you're working on an air conditioning unit. Fortunately, I don't do that. But some of the other things, the technology, the scroll technology, the screw technology, the centrifugal technology has been around for years and years and years. But everyone has found a way to make it a little more efficient. Lighter materials being used, larger components in some cases, so we can move greater quantities of refrigerant in a smaller time frame. Some manufacturers have gone the other way and shrank the components so they can turn them even faster to do the same amount of work. So something to consider, 100-ton reciprocating compressor used to weigh about 1,600 pounds and look like a car engine. Today, you can get that same amount of refrigeration out of a 160-pound piece of aluminum and plastic that turns, again, not 1,800 RPMs, but 36,000 RPMs. They're much quieter. They're much more efficient. Electronics is probably the biggest change that we've seen in our industry. We can do different things because we can vary the speed at which a motor turns to help load or unload to match the system. If it's 100 degrees outside, like where you are in Texas, I need all the AC I can get. But tonight when the sun goes down and the outdoor temperature drops and we have less of a load on the building, I can now just simply slow down the compressor to achieve enough work to keep the building comfortable. In the old days, you would unload a cylinder, but you were still running that 100 horsepower or 200 horsepower motor and consuming the same amount of electricity. So they've definitely gotten a lot more efficient, and that's due mostly to electronics.
Wow, that's really interesting. And I know one of the other things is that systems these days are getting smarter, and you're able to tie HVAC systems into overall kind of smart building type systems more and more these days. What sorts of things are HVAC systems capable of from that perspective these days when it comes to just getting smarter and smarter and not just being more energy efficient, but tying it into an overall holistic building structure of a smarter building?
Another great question. If I was starting in the industry today, I wouldn't have needed to carry as many books on my truck. So the equipment today is actually smart enough that it can generate diagnostics and alarms to tell you not only what is wrong, but the possible causes. And then they can actually communicate that to a building automation system. So someone sitting in Texas who's monitoring a portfolio of buildings in New York could know that there's a problem with the air conditioning system at the Empire State Building before the occupants of the building even knew it was a problem. It allows us to do a lot of remote, not only monitoring, but some triage. So we can tie into a building and log in and kind of poke around and see what's happening, and then arm our technicians with that information before they even set foot in the building. We can read the alarm here and make sure that the guy that shows up has the right temperature sensor or pressure transducer or whatever component it is that we know has failed because the machine told us so. It's really, really interesting. And if you have the right setup and the right personnel, you can really wow the client by showing up prepared and not having to make that second trip once you've now diagnosed the problem and then gone back to get the part to come back again at a later date to do it. We can kind of make this a one-stop shop. It's really cool. Some of the other things that we can do is model building performance, and we can look at what time of day the chiller started and what time did the building actually get to its set point. So we know that, hey, tomorrow it's going to be 10 degrees warmer outside. We need to start this thing 15 minutes earlier or 20 minutes earlier. We can program in lots and lots of offsets to utilize lower ambient temperatures to kind of free cool and get more fresh air or ventilation into the building. We can monitor the environmental quality of the building. What is the CO levels and how many parts per million? What's my fresh air turnover? What can I do to make the occupants of that building more comfortable without them even knowing I've done it? And I can make those adjustments from my home base and never put a man in the building. And the tenant only knows, hey, it feels really good in here. And, you guys are doing a fantastic job.
That's some incredible stuff, and it's just incredible to watch these systems get smarter, right? And learn new capabilities and provide diagnostics, like you said, more predictive type maintenance style things as well. So, Jerry, let's talk a little bit about maybe some of the most common things that go wrong with HVAC systems. What are some of the things that you will see on a more regular basis that fail that maybe people can keep an eye out for, or at least know a little bit more about when it does happen?
The number one thing is a lack of preventative maintenance. So you brought up predictive maintenance, and those are the routine checks that we make to check integrities of motors or tubes or components within the system. But dirty air filters, you reduce the airflow across that evaporator or indoor coil. So now you're going to reduce the temperature of the coil. You're going to reduce the amount of air getting to the space, and it's going to lead to issues. Worn belts or loose belts. You have a motor that's capable of turning, again, at 1,800 RPMs, and it's designed to turn a fan at a given RPM. But if the belt is loose or cracked or frayed, I'm not getting the same airflow out of the unit as when it was brand new out of the box. So cleaning the condenser coils, again, we talked about, the process of taking that high pressure, high temperature refrigerant and cooling it and then subcooling it to make it a liquid to go do the work. If our condenser coils are dirty, and if you live around cottonwood trees or construction in the area or environment, that fan on the roof that's turning to bring that cooler air across the coils is like a big vacuum cleaner. Any trash, any debris on the roof, any dust or dirt in the air is now going to get sucked onto that coil and could form a blanket, and now you're less efficient. You run higher pressures, higher temperatures, you consume more electricity. The unit is apt to break or trip off on one of its safeties simply because you're not moving work. So the deferred maintenance is the number one thing that we see. All the components are made by man. They're going to fail. It's not a question of if, but when. We like to think that we have some very reliable systems, but you still have to put your eyes on it. It's like a car. You wouldn't drive your car around the world without changing the oil once or twice. So, that maintenance is the number one thing. The other stuff, if you have a market where there's power issues, rolling blackouts or brownouts, there are a multitude of devices you can install on your system to protect it from that, a phase monitor or a surge arrestor that sees those conditions and the power change and turns the unit off. It says, hey, we're going to shut down until that power is stable again. Little things like that, especially with all the electronics that are in these units today. It doesn't take much to kill a board, if you took a voltage spike or lightning strike.
So, Jerry, when you have conversations with people about this, maybe people that don't have the same expertise as you, what do people often get wrong, or what are some common misconceptions? I think for me, anyways, just in talking to you, I never knew really about the heat removal process and the transference that needs to happen there. Tell me, what are some of the common misconceptions that you've come up against as you've had conversations with people about this?
Sure. So the biggest one is, hey, I've turned my thermostat down to 50. But it's not 50 in my office or my home. The thermostat is basically a device that wants to maintain a set point range. They usually have an offset or a gain, and if I set it at 72, the AC comes on at 75, it goes off at 69, and I'm going to maintain that 6-degree differential somewhere around 72 degrees. Simply turning it down to 50 just says it's going to run longer. The unit is designed to deliver a specific set point in most cases, or discharge air temperature, and all you're doing is causing it to run longer and waste energy. That ties in great to the folks that take a long weekend and they turn their air conditioning off because they want to save energy, and then they come home to a 90-plus degree house and they turn it on, and now it runs for 3 days because it's trying to catch up and remove all that heat from the home. So, my best advice to those folks is set it at a comfortable temperature and walk away. If you want to do a night setback, you go to bed. You don't care if the house warms up a little bit or cools down. Most programmable thermostats will allow you to program an occupied and an unoccupied temperature. But the deviation should not be 20 to 30 to 40 degrees, because the recovery time to make your space comfortable again and the power consumed to do so will certainly outweigh any benefit of the energy you saved by turning it off.
You know, it's funny. I had a roommate in college who thought that the temperature he set the thermostat to was the temperature that the air would come out of the vent. And so he set it down really low in the summertime because he thought that was the best way for him to cool down.
So now that's an interesting point. So there are, again, multiple types of systems. When you think about a system in your home, it's what we determine as a constant volume system. We move the same amount of air across that coil anytime the fan is running, and we're trying to achieve a space temperature set point. In the commercial market, some of the malls, things like that, we have what's called a variable air volume system, or VAV for short. In a VAV system, the primary unit, the rooftop or the air handler, is designed to spit out a given temperature of air the entire time it's running. And we will vary how much we let into a space. So consider a commercial office building. You know, the sun comes up in the east and you have that huge solar load, and those people are getting cooked. While on the west side of the building, you know, it's still shaded. Maybe not everybody has shown up to work yet, so you don't have the lights and the computer and all the other heat loads. So they don't need as much air conditioning. So in a VAV system, we tell the unit on the roof, spit out 55-degree airs all day long. And then we have air valves in the building that will open and close to maintain the space temperature. So the big reason that is such a popular system is I can make it a little bit smaller. Because chances are not every box, every air valve is going to be wide open at a given time. So I don't need a fan big enough to move the airflow through the entire building, because I'm only going to do a half to 3/4 of it at any given time. As the sun moves around and the solar load now goes to that west side of the building, the east side is shaded or cooling down. So now I need more air on this side than I did on the other. So your roommate had it half right. If you had a VAV system, he was spot on. If it was constant volume, he was mistaken.
Well, I'll need to call him and tell him he may have been right, because I made fun of him at the time. So it's good to know. It's good to know. Maybe he wasn't as wrong as I thought at the time. So, Jerry, you obviously work in the commercial space, right, with office buildings and facilities and that sort of thing. But is there anything that residential homeowners and people like that can learn from what you do in the commercial office space? Is there any advice you can give people who maybe say, I don't know anything about HVAC, I don't really need to because I work in a commercial office building and someone else takes care of that. But they may have, HVAC stuff at home. And is there any knowledge that maybe they can learn from what you do in the commercial space?
Absolutely. So the biggest thing, obviously, we want to keep everyone safe. You don't go into the unit control panel if you're not trained to be around the higher voltages. Most residential equipment is 208 to 230 volts. And if you touch the wrong wire, you could get lit up a little bit. But there are a number of things that folks can do to keep their system efficient. If it's a cooling-only machine, not a heat pump, so you're only running the air conditioning about 9 to 10 months out of the year. That first cool day when you turn it off at the thermostat, go outside and turn it off at the disconnect, and then just take a garden hose. Hose off any grass clippings or leaves from that condenser coil, because again, throughout the year when that fan outside is running, it's pulling any pollen or debris or, grass clippings up onto the coil. So to rinse that off to make sure that your coil is clean when you get ready for the spring again is super beneficial. Inside the condensing unit, if you can get to it, you'll typically find leaves or branches or dead cicadas. Vacuum them out. That stuff shouldn't be there. On your indoor unit, it's crucial to keep the filter replaced, and depending on the age of the home, the construction of the home, you might get away with twice a year, and maybe you have to change the filter 4 times a year. So make yourself a calendar reminder that, hey, every 90 days, let me go pull this filter out and take a peek at it. Again, a dirty filter causes you to consume more electricity, could cause the evaporator and or coil to freeze up in the cooling mode, which then is going to continue to run the system because you can't maintain your set point. And then the other thing, and I highly recommend it, is to get some sort of service agreement, even if it's only one inspection a year, and have someone who's a trained professional who can pick up on the fact that, hey, there's a little oil around this fitting. It could be a refrigerant leak. Or, your unit is 27 years old. You should consider upgrading or adding this component to it. There are lots and lots and lots of trusted or trustworthy contractors out there. To get to know them, contact the Better Business Bureau and see who's real good in your area. And that once a year inspection could prevent you from, hey, it's getting warm out, let's turn the AC on, and it doesn't work anymore. And then the last thing that I'll give you with, unless you have any more questions, is refrigerant in a system never goes away. If your system works today and it's charged with the appropriate amount of refrigerant, be it R22 or R410A or 134 or any combination, unless there is a leak, that refrigerant is going to be there as long as you and I are here. A component failure could harm the refrigerant. It can become acidic, and then, yes, you need a new charge, but you're already doing a repair. But under no circumstances should someone think, hey, let me add a little bit of Freon, which is a trade name, to get my unit working. If you're adding it, it's because it leaked out somewhere else. And if you don't find that leak, it'll just be a continual cycle of, it works good when I put gas in it, and then it doesn't work so great, so I got to put some more gas in it. It's a waste of money. It's less efficient, and it is harmful to our environment. So if someone adds refrigerant, ask them where the leak was.
Excellent questions to ask, and a lot to think about and chew on if you are a residential homeowner or you're renting a house, whatever. If you need AC, these are some pretty amazing tips from Jerry Taylor. So Jerry, thank you again so much for joining us for the first episode of Help Me Understand and helping us understand HVAC a little bit better than we did before. Jerry, it's been an absolute pleasure.
Glad to participate, and hope you get a lot of viewers. And if you have questions, you know how to get a hold of me.
Exactly. If you have questions for Jerry, go to Boland.com, get in touch with him and the team there at Boland, because they are HVAC experts. Like I said, up there in the DC metro area, they know all there is to know about HVAC, and get in touch with people like Jerry. So Jerry, thank you once again. It's been a blast, and we appreciate you joining us.
Thank you, Tyler. Have a great day.
Thanks, you too, as well. And everyone, thank you for tuning into the first episode of Help Me Understand. We hope that you understand a little bit more about HVAC than you did before we started this episode today. And if you want to hear a certain topic, if you have questions about a certain topic in the future that you want to understand a little bit better, get in touch with us. Let us know. My email address is Tyler, Tyler.Kern, Kern, at marketscale.com. Get in touch and let us know what you want to understand a little bit better, and we'll find an expert to help you understand that topic a little bit better. Stay tuned for upcoming episodes of the show. We'll be back very, very soon with more, but for my guest today, Jerry Taylor, I've been your host, Tyler Kern. Thanks for joining me.